Hi, everyone. This is Chunxu Tang from the Twitter Presto team. And today, one of my colleagues, Beinan, and I will give you folks just a tech talk about the Presto at Twitter, which are about some stories pursuing for scalability and availability at Twitter. So here are three major parts of our presentation today. At first, I would like to talk about the story of Presto at Twitter. I will introduce some basic information of Presto clusters. And then I will talk about the story of Query Predictor, which is a quite innovative service that applies machine learning techniques to try to predict the cost of each Presto query. And finally, Beinan will introduce a story of the Presto Druid connector, which will empower the SQL queries on real-time analytics. So let's begin. So first of all, I will talk about the story of Presto at Twitter, which is actually a long path pursuing for scalability and availability. So here are some basic statistics of Presto clusters at Twitter. For now, we have more than 9 clusters, including on-prem clusters and on GCP clusters. We have more than 3,000 Presto workers. And for now, all the Presto clusters have ran more than 10 million Presto SQL queries. And to maintain and develop so large Presto clusters, we have set up a framework called Presto Federation, where we have a Presto router sitting between the client and the Presto clusters. So when the client would like to query a Presto cluster, he or she will first send the query to the Presto router, and the router will tell the specific cluster to query. So in that case, it will give us some benefits regarding scalability and availability. For scalability, it makes it very easy to be scaled horizontally. We can have multiple Presto clusters at one time. And also at the same time, the waiting queue will be split to subclusters. And also at the same time, we have provided aggregated UI and APIs to customers. So for the availability part, as we have multiple Presto clusters, and we also apply the rolling deployment strategy. In that case, even though at one time, maybe one specific Presto cluster is offline, but the client can still query other Presto clusters. So it can also help us to improve the availability of our Presto ecosystem. So for now, we have open sourced all the source code of the Presto router. So here is, we have put all the code on the GitHub, so feel free to have it a try. At the same time, we are applying some basic scheduling mechanism onto the Presto router to schedule these queries across these Presto clusters. For now, there are 2 different mechanisms. One is round-robin approach, and the other is fixed routing. Why we have the fixed routing is that for some specific queries, we may have a very specific cluster. For example, we have a Presto Tableau cluster, which is especially created for Tableau clients. So we also find some problems about this kind of approach. For example, it may cause a starvation problem that we notice that sometimes most all of the queries are quite short, which means that they could be completed in just a few minutes. But we also observed that there are some quite large, very resource-consuming queries, which may cost maybe like a few hours to complete. In that case, these resource-consuming queries may occupy lots of resources in one specific Presto cluster. But as we are using the round-robin approach, some new requests are still forwarded to this cluster. So it will cause some problems like waste of resources and a very long waiting time. And also this kind of information can also be viewed from the aggregated UI that we have provided from the Presto router. So to solve these problems, we are working on an intelligent Presto cluster management system, where we added 2 other components to solve the problem. One is Query Predictor, and the other is Query Scheduler. For the Query Predictor, This is a service to try to predict the cost. For example, the resource usage, the CPU time, or the peak memory bytes of a specific SQL query. And this information will be returned to the Presto router, and the Presto router will utilize another component named query scheduler. And the query scheduler at the same time will collect some cluster statistics from these clusters. So in that case, it can use this kind of information to schedule the queries across this clusters more intelligently. So that's the whole picture of our design, and this will lead to the next story of our presentation today, which is about the story of query predictor service at Twitter. So this is about the story about how to use machine learning techniques to predict the cost of a SQL query. So for the query predictor at Twitter for now, it has been used by many different services. For example, we have created a web app for this query predictor. It can also be used by some BI tools. At the same time, it is used by some notebook tools. At the same time, absolutely, it is used by the Presto router to schedule these queries across these Presto clusters. And here, this is the high-level design of this service. So first, we have some historical queries, and these queries have generated some request logs, which are stored. And then with these Presto logs, we trained two different models with some machine learning algorithms. So these two models are CPU model and the memory model here. The CPU model is used to predict the CPU time of a specific SQL query, and the memory model is used to predict the peak memory bytes of a SQL query. And for now, we have open sourced our code, and it is in the Twitter fork repository. So here is a link of our project. So feel free have a try of this project, and any suggestion will be welcome. And to solve the problem, first we need to define what is the problem that we want to solve, right? So for each query, we want to predict the CPU time and the peak memory bytes. From our observation and our purposes, we don't need to get a very specific value for CPU time or peak memory bytes. What we need maybe say whether this is a large query or like short query, this is a very like CPU consuming query, or this is not a CPU consuming query, right? So in that case, we just need to put them into different categories. For example, for CPU time here, we just put each query into 4 different categories, like shorter than 30 seconds, 30 seconds to 1 hour, 1 hour to 5 hours, and larger than 5 hours. For peak memory bytes, we have 3 buckets, smaller than 1 megabyte, 1 megabyte to 1 gigabyte, and larger than 1 gigabyte. So in that case, we convert a regression task into a classification task, where we can apply different classifiers to train the models. So here is the pipeline of the whole query predictor service. First, we have some Presto logs, and then we will apply some data discretization approach to convert them into some categories, and then we'll do some data cleaning, and then split the data set into a training data set and a testing data set. For the training data set, we'll apply some vectorization techniques, such as the TF-IDF, term frequency, inverse the document frequency, which is a commonly used approach in information retrieval and natural language processing. And then after this step, we'll do some training. Here at Twitter, we especially use a mechanism called XGBoost, which is a gradient boosting decision tree approach. In that case, it will generate some models. And then for the testing data set, we'll do a data transformation based on the vectorizer we have used. And then we'll do some evaluation on the models which have been trained from our platform. So that's the whole picture of the query predictor service pipeline. And then for the model evaluation, we need to see like whether the model we get is good or not, right? So there are some different metrics which could be used to evaluate a model. So here, First, I would like to introduce the accuracy to evaluate these models. And we find that the models are pretty good. For the CPU time, the accuracy is as high as 94.2%. And for the memory model, the accuracy is 92.4%. But here, I also want to mention that accuracy is not always be the best metric to evaluate a machine learning model. Sometimes we also need to consider other metrics, especially for some imbalanced data sets. So for example, here, I also put the precisions and recalls to evaluate these two different models. For example, as we especially care about some really resource-consuming queries, I especially put the CPU time range like larger than 5 hours precision, recall, and F1 score here for an evaluation. So overall, with our approach, we get a quite good models for prediction. And also, we have created a query predictor web app. So here as we have provided a window and where the user can fill in some queries. And then the user can just click the predict button to get some prediction of the CPU time and the peak memory bytes of it. So we have also included this web application in the source code. So feel free to have a try and see whether it can predict your queries. Okay, so in the next part, Beinan will talk about the story of Presto Druid connector.
Thank you, Chunxu. Yeah, next page, please. Yeah, today I want to share the story about Presto plus Druid in Twitter. Yeah, in Twitter we used to use the original version of the Druid connector. It works just like the Presto Hive connector. It used the Druid as a meta store, and it will scan the data on HDFS. For this kind of architecture, it's super good for the table scan, but with this architecture, we cannot use it as a real-time analysis engine because we do some early research on this kind of things. We found if we want to scan 1 gigabyte memory, it will take at least 250 milliseconds. Yeah, so that means if we just do the scan, it's really difficult to reach the latency within 1 second. Even though maybe some query just scan a very small amount of data, you can still not achieve the query within 1 second. So we developed the second version of our Druid connector. It uses a different approach. It pushed down the aggregation and the filter from Presto side to Druid side. Next page. Yeah, so within this approach, that means on the Presto side, we won't scan the data. We take advantage of the computer engine of Druid. We push down the SQL query from Presto to Druid. By doing that, we can generate a SQL, we call it Druid SQL DQL from Presto to Druid. And we take advantage of the Presto connector plan optimizer. It provides an interface just within our connector. The Presto will pass in the logical plan from coordinator to our Druid connector. The logic plan does something on the left. We have something like an aggregation node, a filter node, and a projection node. During our optimizer, we optimize this kind of node. We squash this kind of node together as one table scan node. Actually, in this node, we just send a DQL from Presto to Druid. That means most of the compute part will push down to the Druid part. The Druid will use their own index to do the calculation. So on Druid side, it will just get a very small amount of data and return the result to Presto. And within this approach, we can also make the Druid table joined with some other table like Hive table, Peanut table, and MySQL table. The table used by other connector, you can just use their own optimizer, do the similar optimize. So that means that the Presto just passed in the logic plan for Druid part into the Druid connector. It will pass the logic plan, maybe something like a Peanut or MySQL to the MySQL or Peanut connector. So this kind of optimization can working together. So we can join the data from multiple data sources and also achieve the very low latency requirement. Next page. We also do something on the GC optimization. Actually, we are happy with G1 GC for years because it's really good for the large heap and high throughput. The upper chart in yellow is the Java 11 with G1 GC. We can see generally it's good, but we have some huge spikes with 2000 milliseconds, something like that. So something is not good for the real-time analysis. So we involve the ZGC to Presto. The lower chart in blue is the ZGC. We can see we have a less spikes, and the larger spike is just 60 milliseconds. And most of the GC time is below 20 milliseconds. So that's really good for the real-time analysis. I'm not saying that ZGC is always good because we can also see we have 5 to 10 times more GC count, and we can also see some throughput deduction. But just for the real-time analysis, we can use ZGC to reduce the latency, and we can get less spikes of the latency. Next page. Yeah, it's another task in the Presto Druid connector. We also use Presto to do some data ingestion to Druid. By this work, we can just write one SQL to collect data from other data sources like Hive, Warehouse, like MySQL, like Peanut, and we can manipulate the data. We can join the data with some other tables, and then we can output this data to some storage, like HDFS or GCS storage, and Presto will call some API called Druid indexer, which will load the data we just generated in parallel. By doing so, in Twitter, we can just create a Druid table, or we can say inject data from a Hive data warehouse to Druid within just one SQL. Yeah, it's super easy to do the ingestion job. Next page. The original approach of the Druid ingestion just asked the user to prepare something like an ingestion spec. Yeah. But for the new Presto Druid connector, this spec can be just generated by the SQL. If you select some columns from a data source, it can help you to generate this spec. It can generate the information for each column, like the dimension column as well as the matrix columns. So this kind of spec can be generated automatically by the Presto Druid connector. And the Presto Druid connector will upload this spec to Druid. Druid will read this spec and load the data. Yeah, I think that's all from my side. And yeah, we can go to the Q&A session. Hey, thank you guys.
Thanks, Beinan. Thanks, Chunxu. Talk a little bit more. There's a bunch of questions about the routing as well as the query predictor, and these are two different repos, two different projects, two different things which are also integrated, right? Talk a little bit more about that.
Yeah, sure. The router project at Twitter has been created from last year. So that project is used to, because we have so many different Presto clusters at Twitter, it's very difficult to maintain so many clusters because of scalability and availability. So we have the router project, which is used to route different requests to some specific Presto clusters. But there is also a problem that we have observed while maintaining these clusters, that is sometimes, especially considering there are some really like resource-consuming queries, these queries may occupy too many resources in one specific cluster. But because we are applying roving approach in routing this request to different clusters, sometimes, for example, in one cluster, there are like 2 or 3 quite resource-consuming queries, and these queries may use too many resources in this specific cluster. This will make the whole cluster be like a waste of resources, because one cluster is very busy, but the others are quite idle at the same time. So we had the idea of creating a query predictor service to try to help us to predict the cost of each query beforehand. So we started this project at the very beginning of this year, and we have also open sourced the query predictor project as well as the router project. So the query predictor is directly used to predict the cost, the resource usage of each query. So with this information, and then with our router service, we can route requests to different clusters more intelligently. So that's the whole picture of it. Yeah.
There's another question about rolling deployments, and so how these are done with fixed router predictor strategies. Maybe you can talk a little bit about it.
Beinan, would you like to talk about that, or I can? What's your idea?
I can answer the question.
Okay. Yes. So the thing is that there is opportunity. For example, when we apply, so the first thing is that the router service and the query predictor service are 2 independent services. So they don't have influence. They are not a hard dependency on each other. So, for example, suppose that a query predictor is offline because some like issues, but at this time the router can still work. It may like it may fall back to like the roving approach to route this request to specific Presto clusters. If the one specific Presto cluster is offline, in that case, the router will take care of that. It will just forward request to other available clusters. It is also possible that when the query is executing in one specific Presto cluster, but at this time the cluster is down, in that case, the queries will just be retried from the client side to resend the query to the router and then to a specific Presto cluster. So that's the main story of it.
Okay, thank you. I think there is a question about Prism and the Presto router. I'm not sure if you heard about the Prism update earlier in the day. Do you know how they are related? Are they similar?
I'm not sure.
That's all right.
I'm not sure. Yeah.
We have little knowledge about Prism, but for Presto router, it's just a very lightweight, routing system for Presto. Yeah, it's easy to use and easy to deploy, and it's transparent to the users. Yeah, so there's no burden from our client side. It's just like a normal Presto interface.
Got it. A question on the query prediction. And so do you consider I/O requirements? Did you consider I/O requirements for executing the query and the associated costs?
I see. Yeah. For now, we don't consider I/O. There are 2 things we are predicting. The first one is the CPU time of each SQL query, and the other is the peak memory bytes of each query, because we find that these 2 metrics are quite crucial for the prediction. the incoming Presto queries. Yeah.
Got it. I think that there's a related question on what happens if when a query is predicted to use more resources, right? What happens if that's the case?
I'm not sure whether the question. I understand the question correctly. I guess the question means that what's if the query is predicted to need more resources over the cluster can offer to it. So in that case, the answer will be that when we do the classification, we need to have some buckets. So in that case, we'll just this situation usually won't happen because the bucket is defined based on how many resources we have. So, but there is also a chance that, for example, the maximum, so for example, the memory is 10 gigabytes, but the query may need like 11 gigabytes. In that case, the query will just fail. So in that case, the client may retry or will let the client know that the query consumed too many resources, so that the user may need to use, for example, may need to like optimize the query to consume less resources on it. Yeah.
Got it. Thanks, Chunxu. A question about the scheduler. Can you share a little bit more about the scheduler that you're using within the Presto router, or are you just leaving it to the coordinator, the Presto coordinator?
Beinan, would you like to talk a little bit about it?
Actually, we don't have a scheduler inside the Presto, right? But in Twitter, our customers actually they're using various scheduler, something like Zeppelin, like Tableau, or some cron jobs, or some ETL job just made by themselves. Yeah, they can be from anywhere. They are using some Presto query to generate their production data or something, maybe some very critical jobs. Yeah, this kind of query can be scheduled by their application, not on Presto or router.
Right. So the router is essentially just handling the workload that's sent to it. Right,
sure,
and then and then the queries are the coordinator takes care of the rest.
Yes,
once it's routed to the right cluster.
Yes, true. We just want to split the waiting queue to multiple queries, and also in Twitter, a lot of our customers they love the UI, they love the Presto UI, but the Presto's UI is really heavy sometimes. They don't make drag the Presto coordinator down. So we also use this router to handle maybe 99% of UI request. So our customer can just visit the router to see the status of their queries.
Got it. Thank you. Let's take one last question and then wrap up. There's a question about use cases. So you're obviously using a range of different connectors and systems. You're using Kafka, Druid, Data Lake. Can you talk a little bit more about the use cases, analytical, or would you use Presto for ETL jobs as well?
Yeah, that's a good question. In Twitter, at the very beginning, we designed, or we can say we involved Presto to Twitter just for the ad hoc queries as other companies. Right? The user just send some employee query to Presto, and they can just reading maybe from their data visualizer or Zeppelin. They can see the results in a couple of seconds. But we are running Presto really well, and the service become very stable. So more and more customers want to use Presto to do some data ingestion. Someone just use Presto to collect data from Hive warehouse and write data to some other data source, like Vertica or something else. Yeah. So then they have something like ETL job, but I have to say it's not real ETL job. It's just some guys make something for their easy implementation, because it's really convenient. Just use Presto. Presto can scan multiple data sources and collect the data together. And also Presto have a strong, we can see some data ingestion features. So we can just implement something like the Druid connector. We can ingest data to Druid, something like that. Yeah. So I have to say 99% are still
queries are still running on the head warehouse, data warehouse. But some corner case, we cannot corner case, just some user also use Presto for some ETL job or data ingestion.